So today we are going to be talking about the concept of mesh analysis. Mesh analysis is extraordinarily similar to nodal analysis, except that we apply Kirchhoff's voltage law multiple times to perform mesh analysis. Okay? So we are going to learn about this process by working example problems, much like we did for nodal analysis. And our first circuit that we are going to look at is this one. We're going to have a 10-volt source. Like so. We will place a 2-ohm resistor here. A 4-ohm resistor here. A 1-ohm resistor here. A 7-ohm resistor here. A 3-ohm resistor. An 8-ohm resistor. A 6-ohm resistor down here. And let's put a 9-ohm resistor in the top left. And a 5-ohm resistor in the bottom left. Like so. All right, so the first thing that we are going to do is we are going to identify our meshes. This is probably even easier for us to do for mesh analysis than it was for us to define our nodes for nodal analysis. Okay, so let's put number 1. Identify meshes. Okay. So the first mesh that we have, I'm just going to start from the bottom left-hand corner, go up like so. And come back across like this. So this is our first mesh where, if you recall, a mesh is nothing more than a loop that doesn't contain any smaller loops in it. We also have a mesh here. And a mesh here. Now, what I'm doing here with these arrows is I am assigning a particular direction that I believe the mesh currents that we are about to label flow, okay? So I have made an assumption here that there are going to be 3 mesh currents because there are 3 meshes, and I am just assuming with no indication as to why really, that these mesh currents are going to flow in a clockwise direction around their meshes. You do not have to follow this convention. You can choose your mesh currents to be counterclockwise as opposed to clockwise. You can even choose your mesh currents to be a combination of the two. I would argue though that the more difficult you make it, meaning if you don't use all clockwise or all counterclockwise, the more likely you are to make some sort of mistake. I was taught to assign all of my meshes in a clockwise direction, so that's the way that I do it. I understand that I think the moment of inertia is typically drawn with a counterclockwise loop or arrow, so some mechanical engineers prefer to go that route. Whatever works best for how you process information is fine by me, but consistency is very, very important to doing this well. All right, so we've identified our 3 meshes for this particular circuit. The next thing I'm going to do is I'm going to label or assign my mesh currents. So I'm simply going to give each of these 3 different colored currents a name. That's all that this step is. So I'm going to call this first mesh current IA, the second mesh current IB, and this third mesh current IC. Now, our third step, which we're not actually going to do in this particular problem, is very similar to what we would do in a nodal analysis problem. We would express our controlling variables in terms of our mesh currents. So I don't have a dependent source in this particular problem, but what I can do is throw out some variables that we might be interested in, okay? So for example, let's say that we were interested in knowing the current flowing down through this 4 ohm resistor, which I'm going to call IX. And we were also interested in this voltage drop across the 1 ohm resistor, which I'm going to call VY. Okay. How could we express the current IX in terms of our mesh currents? Well, as our red mesh current IA flows around its clockwise path, when it's flowing through the 4 ohm resistor, it's in the same direction as IX, so it's going to get a positive sign. So we would have IX is equal to IA. And as we follow our green mesh current IC around its clockwise path, when it flows through the 4 ohm resistor, it's flowing in the opposite direction of IX. So it's going to get a minus sign. So we put minus IC here. And that's how we would define a current in terms of our mesh currents. Now let's look at our voltage VY. Okay. So for our voltage VY, we would just use Ohm's law. We have a 1 ohm resistor. The current flowing into the positive polarity terminal is IB, and there is no opposing mesh current flowing into the negative polarity terminal. So we would write that as IB minus 0, or simply 1 ohms times IB. So that's how we would define controlling variables in terms of our mesh currents. And I chose to give you an example for both a current in terms of mesh currents, as well as a voltage in terms of mesh currents, as we'll be seeing those things over and over and over again throughout today's lecture. Okay. All right, so from here, once we have expressed our controlling variables in terms of our mesh currents, we would move along to step 4, where step 4 is to write a KVL equation for each mesh current. So how I do this is I simply start at the bottom left-hand corner, like I did for our KVL loops when I first introduced the concept, and I simply follow the current around its clockwise path. I assume for resistors that my mesh current is always flowing into the positive polarity terminal of the resistor, and then any opposing mesh current, as we'll see in a moment, will be flowing into the negative polarity terminal, so it'll get a minus sign associated with it. So let's start by looking at mesh current IA. So KVL around mesh A. The first thing that we see, if we're starting from the bottom left-hand corner, is the negative polarity terminal of the 10-volt source. So we're going to write that down as minus 10 volts. The next thing we see is the 9 ohm resistor. And we're always going to assume that the mesh current we're following is flowing into the positive polarity terminal. So this is going to be 9 ohms times IA. The next thing we see is the 2 ohm resistor, and now we have 2 currents that are flowing through the 2 ohm resistor, okay? Since we're following IA, we're going to have positive IA flowing through the 2 ohm resistor, and IB is flowing in the opposite direction as as IA as it flows through the 2 ohm resistor. So this is going to give us 2 ohms. My stylus will write times IA minus IB. Then we see our 4 ohm resistor, and we have a similar case. So we're going to see 4 ohms times IA minus IC in this case. And lastly, we see our 5 ohm resistor, and the only mesh current that's flowing through that is IA. And we've now reached the same point that we started at, and so we set this equal to 0. So here's our first equation. Now we would write a KVL equation around mesh B, where we will follow mesh current B, or IB, as it flows into the positive polarity terminal of every resistor it sees, okay? So the first thing that mesh current B sees, as we follow it from the bottom left-hand corner of mesh B, would be the 2 ohm resistor. Since mesh current IB is now flowing into the positive polarity terminal, we're going to have IB minus IA. Then we see our 1 ohm resistor. Scroll up here real quick. For the 1 ohm resistor, IB is the only mesh current flowing through it. So we'll have 1 ohm times IB, and we can see that the next thing we'd see would be the 7 ohm resistor, which also only has a mesh current of IB. So 1 ohms times IB plus 7 ohms times IB. And then we see our 3 ohm resistor. IB is flowing from right to left, which we're considering positive in this case. IC is flowing through the 3 ohm resistor from left to right, so we're going to give that one a negative sign. So plus 3 ohms IB minus IC, and we have reached the node that we started from. So again, we set it equal to 0 and move along to our next expression. So KVL around mesh C starting from this bottom left-hand corner, we see the 4 ohm resistor first. We're following IC around, so it gets the positive sign. IA is in the opposite direction. So we're going to see 4 ohms times IC minus IA. Next, we see our 3 ohm resistor. So we're going to have 3 ohms times IC minus IB. Next, we see our 8 ohm resistor. The 8 ohm resistor only carries a mesh current of IC. And down there at the bottom right, we also had our 6 ohm resistor, which was also only carrying a mesh current of IC. So we have 3 equations, 3 unknowns, and we can then plug this system of equations into our calculator and solve for our various mesh currents. So let's just write step 5 as solve our system of equations. And in doing so, we would find that our mesh currents IA, IB, and IC come out to be 0.534 amps, 0.109 amps, and 0.117 amps, respectively. So that's how we perform mesh analysis for a circuit that only contains voltage sources. Much like what we saw in nodal analysis. In nodal analysis, we saw that whenever we had a voltage source in our system, we would have to adapt our procedure to be able to handle that. Well, here, anytime we have a current source in our circuit, we're going to have to adapt our procedure to handle that. And there are actually 2 different ways that we go about it, depending on where the current source is located. So I'm going to draw a new circuit. And we are going to walk through the steps of analyzing this circuit and show how our mesh analysis procedure needs to change. Excuse me. So this is our new circuit. Let's put a 4-volt source over here on the bottom left. 3 ohm resistor here. We're going to include a dependent source in this case. Will be a current controlled voltage source having a value of 2ix. I'm going to have an independent current source carrying 5 amps in series with a 2 ohm resistor here. Let's put a 5 ohm resistor down here through which a current Ix flows. Four ohm resistor here. A 6 amp independent source down here. Oops, erased a little more than I meant to. And across the top here, let's put a single 10 ohm resistor. So I'd like to get some feedback from you guys, if that's okay. The first thing that I want to know is quite simply, how many meshes do we have? 4. Thank you, Devarier. That's absolutely correct. So we have this mesh on top. Like so. This mesh here on the bottom left. This mesh here on the bottom middle. And this mesh here on the bottom right. So we've taken care of step 1. Identify our meshes. Step 2, still assign mesh currents. So let's call this guy up top IA, and this guy IB, this guy IC, and this guy ID. Step 3 will be to express controlling variables in terms of mesh currents. I'd like some assistance from you guys on this, if you don't mind. Devarier says that it is IX is equal to ID minus IC. I disagree with you slightly. You're very close to Devarier. So let's take a look at it. Okay. So as IC is flowing around its clockwise path, when it hits the 5 ohm resistor, it starts flowing down, which is in the same direction as IX. So that means IC should have a positive sign. When ID is flowing through the 5 ohm resistor, it's flowing up, opposite the direction of IX. So it should be receiving a minus sign. So we should have IX is equal to IC minus ID. Catherine, you got a little bit ahead of me, but you've made a wonderful observation that's going to bring us to our next step. Okay. So what Catherine observed is that our current ID is equal to 6 amps. Okay, so that brings us to step number 4. We're going to write current relationship equations. For each current source. And as Catherine said, ID will be equal to 6 amps, okay? So she came up with this, or at least I'm going to say that she came up with this, by observing that as ID flows around its clockwise path, when that mesh current goes through the branch that includes the 6 amp source, the direction of the mesh current is in the same direction as the current source, so it's literally the same current. If I had defined the 6 amp current source to have a current flowing up, we would have observed that our mesh current is in the opposite direction as the source, and it would have been negative 6 amps, okay? So we have a second current source though, our 5 amp source smack in the middle of the circuit. Actually, before we address that, I wanna mention something else here. This 6 amp source is an example of a current source that is on the perimeter or the outside edge of the circuit. So it will always be able to be expressed in terms of only one mesh current because there is no opportunity for a opposing current to flow against it. Whenever we have an interior current source like the 5 amp source, there are going to be 2 mesh currents that flow through it because the 5 amp, or excuse me, the branch containing the 5 amp source is shared between meshes A and meshes C. We should see that we're going to express our 5 amps in terms of mesh current IA and mesh current IC. So as we follow mesh current A around its clockwise path, when it's flowing through the branch containing the 5 amp source, IA is flowing from right to left, which is opposite the direction indicated by the current source. So IA is going to get a minus sign. When we follow IC around its clockwise path, it's going to be flowing from left to right through the branch containing the current source, or the 5 amp current source, which is the same direction as the current source is indicating. So it's going to get a positive sign. So from this, we should see that IC minus IA is equal to 5 amps. Is that clear to everyone? Just doing the exact same thing that we did when we expressed IX in terms of mesh currents in the previous step. All right, so what we're going to do now is we're going to write a KVL equation for all what I'm going to call super meshes containing interior current sources. That's not how you spell interior. And I'm going to have to abbreviate current source because I ran out of room. All right, so I want to talk about what I'm doing here. We're not going to go into as much detail as I did explaining super meshes last Thursday. The concept is extraordinarily similar. Okay, so I'm just going to outline something in gray here to kind of show you what I'm talking about and erase some of this stuff to make it slightly less busy. So As I try to write my Kirchhoff's voltage law equation around mesh A, the first thing that I would see would be my 10 ohm resistor. I wouldn't have any problem whatsoever there. Okay? So I'd be able to write my my voltage law, or excuse me, my Ohm's law equation for the voltage drop over the 10 ohm resistor and move along about my day, no problem. And then the next thing that I would see would be the 4 ohm resistor. And again, I wouldn't have any issue whatsoever. The next thing that I would see would be the 2 ohm resistor. I would not have an issue. And then I'd run into my 5 amp source, okay? And so we'd be trying to write an equation that gives us the voltage drop across our 5 amp source in terms of our mesh currents. And there is literally no relationship that exists to satisfy this requirement. So we've run into a bit of an issue. So what we're going to do instead is we're going to combine meshes, okay? So in this case, our 5 amp source is shared between mesh A and mesh C. So we're going to combine these two meshes into a super mesh. And I'm going to do that by simply writing the smallest possible loop here that avoids taking the voltage drop over the 5 amp source, which is the loop that I've outlined here in gray. Okay. Now, this loop does not include the voltage drop over the 2 ohm resistor. Okay. But that's actually perfectly okay, because the sum of any, the sum of the voltage drops around any closed loop must be 0. So the sum of the voltage drops around 2 closed loops has to be 0 as well, because 0 plus 0 has to be equal to 0. So effectively, if we had written this for 2 loops and then added the loops together, we would find that the bit for the 5 amp source and the bit for the 2 ohm resistor would exactly cancel each other out, just like we observed when we dealt with super nodes in our last lecture. Okay, so we're doing something extraordinarily similar here. It's just with KVL equations as opposed to KCL equations. So let's formally write our equation around this gray super mesh loop. All right. So the first thing that we see is the 10 ohm resistor. So we're going to have 10 ohms. The only mesh current that's flowing through it is IA. So we have 10 ohms times IA. The next thing we see is the 4 ohm resistor. Since we're following mesh current IA in this part of the super mesh, IA is going to get a positive sign. And since ID is in the opposite direction, it's going to get a minus sign. So we're going to have 4 ohms times IA minus ID. Now, as we follow our gray path here, the next thing we see is the 5 ohm resistor. And at this point along our super mesh path, we are now following mesh current IC. So we're going to have 5 ohms times IC minus the opposite current ID. Then we would see our dependent voltage source. We see the negative polarity terminal first, so that's going to look like minus 2ix. And then we see our 3 ohm resistor. And when we're looking at the 3 ohm resistor, we are again following mesh current A around its clockwise path. So we're going to have 3 ohms times IA minus IB. Set this equal to 0. We don't have any other super meshes to write KVL equations for because we don't have any other interior current sources. Okay. All right, so the next step will then be to write KVL equations for all remaining regular meshes. So we're going to have a KVL at mesh B equation that we need to write. So when we start in the bottom left-hand corner, the first thing we see is the negative polarity terminal of the 4-volt source. So that's going to look like minus 4 volts. The next thing we see is the 3 ohm resistor. Since we're following mesh current IB, it's going to get the positive sign. So we're going to have 3 ohms times IB minus IA. Then we see the positive polarity terminal of the dependent source. So we're going to have plus 2IX. And set this equal to 0. And I want to do something here real quick. I have an equation for IX. So that's equation number 1. I have an equation for ID. So that's number 2. I have this guy right here. IC minus IA is equal to 5 amps. So that's equation number 3. I have this KVL equation for my super mesh. That's equation number 4. And finally, I have this KVL equation around mesh B. That's equation number 5. Our system only has 5 unknown currents: IA, IB, IC, ID, and IX. So we don't actually have to write a Kirchhoff's voltage law equation for mesh current, for mesh D. And in fact, we actually can't, okay? Whenever we have a perimeter current source, there is no loop or path that we can take that could avoid taking the voltage drop over that 6 amp source. So it turns out we will never write a KVL equation for a mesh or super mesh that contains a perimeter current source, okay? We will only have a current relationship equation for that particular mesh, which is this equation right here, which Miss Catherine Weldon pointed out to us earlier. At this point, we would simply move on to step 7, solve our system of equations. And in doing so, we would find that IA was equal to 33 over 19 ohms, or excuse me, amps. IB was 203 over 57 amps. IC was 128 over 19 amps. IB was simply 6 amps. All right, so These two example problems, these two example problems that I've worked here today effectively illustrate all of the different things that you might see when performing mesh analysis on a circuit. So I don't have anything else prepared, but I am happy to provide another example problem or something like that, or just answer any questions that you may have. If you don't have any questions or you wouldn't like to see me work further examples, feel free to log off. For anybody that has a question or wants to see me work another example, stick around and tell me what you want me to do. Sure. So Devarier asked if I could explain about the test dates again. I would be happy to. Okay. So your exams in this class. Oh, and Christopher Smith asked, this material will be on the exam. That is true. This material will be on the exam, as well as the material that we were going to cover tomorrow will be on the exam. Okay. And then Devarier asked if I could explain the test dates. So in this class, the exams will be handled fully over Moodle using the Respondus lockdown browser. If you go to Moodle and click on where it says exam 1, I have put a little, I think it's called a quiz according to Moodle up, where it will force you to download the Respondus lockdown browser, go through all of the initial checks and things like that. And then it's a very, very brief quiz just to get you familiar with how exam questions and things like that are going to look on Moodle. I would encourage all of you to attempt that practice Respondus lockdown thing sometime in the next couple of days to make sure that you're not going to have any issues before you attempt your exam. Now, regarding the exam dates, you are allowed to choose your own adventure. Okay, I am going to put, I believe, 8 different versions of the exam up. One will be available on Thursday afternoon during our regularly scheduled class meeting. So I will have that exam open up at 2 p.m. and I'm going to have it close at 5 p.m. You will only be allowed 2.5 hours to take the test. So I want to be specific about this. This exam is designed to be taken during a 2-hour class meeting, like the exams during the regular year. I am giving you an extra half hour to work on the exam because you are going to have to redraw the circuits and things like that. So I'm trying to give you an extra 30 minutes for the extra little bit of work that you're going to have to do drawing the circuits, because I'm not providing a piece of paper with the circuits on them for you. Okay. So anyway, there's going to be an option for those of you that wish to take the exam between 2 and 5 on Thursday. There will be an option for people that want to take the exam between 5 and 8 on Thursday. There will be similar options for Friday and Saturday and Sunday, so that there are 8 different opportunities for you to take your exam. If by some strange coincidence, none of those 8 options I am giving you works with your schedule, which I would honestly be flabbergasted if you told me that, but things happen. If you cannot make any of those 8 different options, please let me know via email at your earliest convenience, and we will figure something else for you to do out. Whether that be give you the exam at an earlier time on one of those 4 dates, or something can be discussed later. But I'm hopeful that the overwhelming majority of you, if not all of you, will find one of those 8 times to take the exam convenient for your schedule. Was that a sufficient explanation, Devarier? All righty. I will continue to hang out on Zoom if any of you have any questions or anything. just let me know.